we're now going to talk about pyrolysis, or I'm sure they'll explain how to pronounce it better than I. We have three people who are fundamentally involved in the development of this technology. We have Alex Barnes, Director of Barnes & Associates. We have Stefan Peters and Klaus-Dieter Mauthner from CARBOTOPIA, and Christopher Brown.
Thank you, Christopher. Can everybody hear me clearly? Great. Okay, super. Okay, so I'm going to give a brief overview of what is pyrolysis, because certainly I hadn't really heard of it very much until last year, but the more I've dug into some of the literature, the more I've realized there's been an awful lot of work going on it. And I'd just like to use that to make an overall point. As the previous speaker said, we're developing new supply chains and new technologies, and I think the object of the exercise is to decarbonize. So at this stage, given that we are at this kind of embryonic stage, I think one of the concerns I would have is if we're saying we're going to go down one particular route, like choosing green hydrogen. Because whilst green hydrogen may have no carbon production or no CO2 production, on the other hand, there are other factors that you need to take into account in decarbonization, which is cost, how quickly it can be rolled out, etc. And I think this is why creating space for other technologies is important. Now, hopefully you can see the next slide. So what is pyrolysis? It sounds like a fancy name, but basically all it is the thermal decomposition of materials in the absence of oxygen. And this is something which has been around a long time. The making of charcoal has been around for centuries, if not millennia. But in the case of natural gas pyrolysis or methane pyrolysis, basically the equation takes CH4, which is methane, and produces solid carbon and hydrogen. And this is where it differs from steam methane reforming, which you'll hear about later. Now, various technologies have been developed over the years, and in the slides that will be provided after the event, I've got additional slides which give some background history on that. But for example, the Caverna carbon black and hydrogen technology was commercialized in the 90s to produce carbon black. Now, the big change that has occurred in recent years is, of course, producing hydrogen or without producing CO2 emissions has become much more important. Previously, that wasn't an issue, so of course, methane pyrolysis wasn't necessarily in the running. But now that carbon emissions are so much more important, that's obviously a key consideration. But pyrolysis of various materials has been around a long time. And interestingly enough, you can also use other inputs like waste, etc., to also produce carbon and hydrogen. So, for example, breaking down other materials. So to put it in context, one of the reasons why we're talking about decarbonizing gas is that gas is a major part of the European economy. And we heard earlier about difficult sectors to decarbonize. Now, just to give one simple example, I'm sitting in a very ordinary terraced house in London. It was built in about 1890. And with the best will in the world, I can't insulate it any better than I already had. And it would cost an awful lot to put in an air source heat pump, and it probably wouldn't work that well because the thermal insulation of the house I live in isn't very good. So that is, as I say, one of the other considerations when we're talking about decarbonization is how best to do this, and hydrogen could form part of that equation. Now, looking at the different ways of decarbonizing gas, I've mentioned methane pyrolysis. Now, as I said, no CO2 emissions. It produces solid carbon, which is easier to transport and store. For example, you can store it in the ground. It doesn't leach like chemicals. It doesn't require water use, and it can be done at a competitive cost based on the knowledge at the moment. The issue obviously is, as with all technologies, and as the previous speaker mentioned, there's considerable scope for learning by doing. It also doesn't use water, unlike steam methane reforming or electrolysis. Steam methane reforming is also very competitive cost, but you have the issue of carbon capture and storage. Electrolysis has the advantage of no CO2 emissions, but obviously the carbon footprint depends on the electricity source. Now, in 2019, 14% of European electricity generation was still coal, which from a carbon point of view is about as bad as you can get, because obviously that included lignite. I think the other issue I would say in terms of practicalities and stuff, we haven't managed to decarbonize our electricity generation despite sort of well over a decade of trying to do it. And yet we also need to build lots of renewables for the electrification of the wider economy, which is also going to be important. So the issue is the practicality of how quickly you can reduce emissions. And it's not just about the annual emissions in 2050 that's important. It's the amount of CO2 that you emit in the 30 years between now and then, because of course CO2 stays in the atmosphere for decades or hundreds of years. And last but not least, you have biogas, which again can use agricultural waste or other forms of waste, but the resources for it are relatively limited. But I think from an overall decarbonization point of view, you should be trying to be thinking of a way that you could allow all of these technologies to compete to get the best result, rather than, for example, trying to pick winners at a very early stage in the process. Now, in terms of methane pyrolysis, the value proposition, you obviously have plentiful reserves of natural gas. You have a thermal reactor. Now, the reaction requires energy, as it does for the other technologies, but this can actually be provided by renewable electricity as well. So again, we're at very early stages of all of this, but it shows that it's not as sort of black and white as you're just using one particular energy source. There's scope for optimization if the technologies are given the chance to develop. And then in terms of the output, you get obviously hydrogen, which has a value. There's the heat used in the process, and there's the solid carbon, which I'll come on to in a minute. But all those outputs have value. Now, this next slide, hopefully, I know there will be several real experts in the audience. This is the bit where I wish I'd listened more to my chemistry and physics teachers. Basically, as I understand this, this means that in the reaction that you use to get the hydrogen, you need less energy to do it. And this compares the different processes. Now, clearly, there are also a lot of other factors to take into account in total costs in terms of capital cost, etc. But what I would say is I think this is one of the areas which shows that methane pyrolysis can have certain advantages. Now, in terms of costs, obviously, because we're at relatively early stages, there's still a lot of research going on. But this is a slide from BASF, well-known European company who's done a lot of research on this. And I think that's another point, that if we're talking about support for European industry, there are European companies who've done a lot of work on this, and this is potentially, a world-leading technology. But here you can see the different production costs based on their research compared to the capacity of the plants. And obviously, the bigger the plant, the more hydrogen you're going to produce. All these slides will be made available. This is another look at different costs. Now, in this slide, this is produced by a group called ThinkStep, a research organization called ThinkStep, and again, they've looked at various costs, etc. I think the point here at this stage is you can look at the different costs of steam methane reforming water electrolysis, and TDM stands for thermal decomposition of methane, i.e. pyrolysis. Now, there are different technologies, as you can see there, and different groups are looking at the different technologies, but it gives you an idea of the relative scale of the costs. Now, in terms of the case for methane pyrolysis, as I've already mentioned, no CO2 emissions. Again, I think the previous speaker, Stefan, made a very good point that we're building brand new supply chains. And I think this is a point that is not necessarily realized. With decarbonizing, I think a lot of the public focus is just on, oh, well, you produce more renewable electricity. but we're going to have to fundamentally rethink our various energy supply chains. That means getting various people to invest. I was mentioning the case for methane pyrolysis. Now, with CCS, and I actually saw somebody raise this in the questions on the discussion forum, is that appropriate? It is true that CCS can be applied in certain areas because, for example, access to depleted oil and gas fields, etc. But in other areas, it's not always considered politically acceptable. So in a study that Poiri did, and I think they've now rebranded as AFRI, they did a study looking at how methane pyrolysis could help the rollout of hydrogen in areas where there wasn't CCS. Other points I'd like to pick up on: potential for negative emissions if used with biogas. So, of course, obviously, biogas, is not taking fossil fuels, and it's negative emissions because you're then capturing the carbon that's produced from naturally produced methane, for example. In terms of the economic value of the solid carbon products, and in the slides that the more extensive pack, there will be a table showing some of the uses and values. Carbon black, most people will know this from the fact that it's what they use to make car tires look nice and shiny and black. But it's also used in dyes and inks, for example, in printers and plastics, so widely used. Synthetic graphite. Now, graphite is naturally mined, but mainly in China, but graphite is very important for electrodes for furnaces, for steel furnaces is one particular use, but also in batteries like lithium-ion batteries, which, of course, are part of the sort of whole electrification of the economy. Carbon fiber, I think people are probably more familiar with. It's very light, very strong, so its advantages in use of wind turbines or automotive, reducing weight but increasing strength, obviously reduces energy loss. And then graphene is this new super material, which is very, very thin molecular layers of carbon and used in flexible electronics and solar cells. Now, there are other uses, like, for example, people have looked at using solid carbon in concrete and so forth in construction. I think the point here is if you have a lot of solid carbon being produced, then clearly people find a way of using it, and it becomes part of what the EU has said it wants, which is the circular economy. Battery 2030 is the EU program for making sure that the EU has its own capability in manufacturing batteries, and I mentioned about electrodes. And then the new industrial strategy, I think we already heard about how the recovery package will include support for hydrogen. So last but not least, some recommendations, and this will pick up a couple of things that I said earlier. Firstly, I think one of the problems that I've had with the decarbonisation approach to date is the fact that it's tended to favour technologies and it's focused on renewables, which has been great in accelerating the renewable market. But the fact that we still have 14% coal in the electricity mix, and that's the electricity mix, not the overall energy mix, is perhaps less good.
Alex, sorry to interrupt. This is Christopher. Could you finish in a couple of minutes?
I'm just coming to the end. So the second bit is reviewing the EU gas market framework. The point about the third gas package was it liberalised a mature market with established value chains, and there was also an established economic case for natural gas. It did things that other fuels couldn't do, and it could do them better or more cheaply. Hydrogen is an embryonic market, so just doing a cut and paste of one to the other until the market is established is a different case, I think. I think as part of that, it's to ensure level playing field between the different technologies. So, for example, electrification, you just build more generation, more renewable generation, and more transmission and distribution wires, and that's building on an existing framework, an existing market, whereas zero carbon gases, as I mentioned, that doesn't work. And last but not least, I think clear approach for decarbonising the economy. The ETS is great for those areas which have to pay for emissions allowances, but I'm not sure how it works to persuade all those people who heat their homes how they're either going to switch to a lower carbon fuel or upgrade their heating systems to use heat pumps, etc. And on that, I'll finish.
Thank you very much indeed, Alex. I've already got some questions for you, but I'm going to leave them until the next two speakers have finished, because perhaps they'll answer some of them. Just as a heads up to the next two speakers, Stefan and Christopher, a couple of the questions that people have asked is the relative CapEx-OpEx split between methane reforming and CCS versus pyrolysis, and do we have enough physical usage of what to stick the solid carbon that would be produced in large-scale pyrolysis? Would it be possible to use the carbon black in a useful way? Stefan, perhaps you'd like to take the floor. Tell us a bit about CARBOTOPIA and the technology behind pyrolysis.
Okay, can everybody hear me?
Yeah.
Hello?
Yes, we can hear you.
Okay, so most recently, there's the new term, the climate neutrality. And actually, if we look at nature, we're always tempted to be carried away by the abundance of nature. But actually, that stops at carbon and water level. And the biggest sin we are currently committing is that anything we throw away, we are not really aware that the away is air today. Whether we burn it, generating CO2 and water vapor, or let it rot, which makes it even worse because it generates additional methane, being a very aggressive greenhouse gas. Now, where does the methane come from? Nature is a very simple concept. It uses three elements, carbon, water, and hydrogen. Carbon, hydrogen, and oxygen, the latter two coinciding as water. So basically, we have two building blocks. And nature builds energy matter up from water and carbon. And at the end of life cycle, it decomposes everything into gases made from the same three atoms. And because energy never can get lost, it's inherited by methane, CH4. And the transformation loss is CO2. And the mass balance is water. So to keep the carbon and the water cycles in balance, we have to make sure that we stabilize this methane. And there, the methane pyrolysis is a very good stabilization by giving the ability to put it into storable carbon. So coming from there, we have worked together in the last 7 years with groups in the university sector in Vienna, occupying in transforming carbonaceous matter accelerated into energy-rich gases. Now, the problem is that this has been even demonstrated at large scale in an Air 300 project at Gobi Gas, which is commercially a disaster, but technically actually validated. Now, the reason why it's a disaster is because the product gas is very vulnerable to the input feedstock mix, and therefore to make commercial value of the output gas is very difficult without homogenizing the output gas. And it turned out that if we put our thermo-decomposition of methane, we always called it, therefore nobody finds us when looks for pyrolysis, methane pyrolysis in the literature. Although we've been in the patent regime since more than 20 years with this, actually this enables to homogenize the output of accelerated decomposition of energy matter. So as we see it at the moment in Europe, there are the very high temperature plasma approach at BASF. From what I've seen, I wouldn't give it more than TL3. There has been Carlos Rubia, who told everybody that the way to
Yeah.
So ours we call the continuous catalytic chemical vapor deposition technology. Actually, we had started 20 years ago working on this technology. But in the late 2000s, we built the first reactor, and it validated in a uninterrupted continuous industrial production for making nanocarbon products for more than 6,000 hours. So actually now we have worked on redesigning the catalyst system to enable a vertically fluidized bed methane splitting. However, that new catalyst system is validated at TL4, and we need the scale-up engineering yet to be done. That's why I say to go into scale, anybody who wants to work with us will need to account for 24 to 30 months, but then we have a real viable production. And as I already mentioned, the concept of decarbonizing using this technology, we had already published in the Leibniz Institute journal in 2007. So the hydrogen production cost in the different methods comparatively, I've tried to benchmark against each other at very favorable energy cost and utility cost assumptions. But the important thing that I think needs to be considered is that for the methane pyrolysis, we can counter account the revenues that are achievable with the carbon. Now, here again, I have been coming from the carbon side because that's where our development originated from. And the question of the accommodatable amount of carbon in applications has always been a showstopper. So therefore, we targeted to reach a cost level where we could afford to sell that carbon at a crude oil equivalent carbon price, which is 1% of a barrel crude oil price. And that's computed in there, okay? So later in the addendum, there is the table with the figures as well. But anyway, using the methane pyrolysis in carbon circularity to neutralize the blue hydrogen economy means that if we do a grave-to-cradle carbon circularity, 50% of the carbon that is reused as an oil or coal substitute in non-combustion chemical applications, 50% of that will always stay stored in the matter over several consecutive life cycles. And that means if we have a certain amount of grave-to-cradle carbon, we can afford to double that with carbon from a blue hydrogen pyrolysis, because if we reuse it for non-combustion oil or coal applications, we can say that the blue carbon will never be sent out to the atmosphere. Now, it makes much more sense to do a grave-to-cradle carbon economy than producing CO2 and resurrecting it with hydrogen afterwards, because just only the water needed for that is enormous. Nobody seems to pay attention to that. But basically, we would need 6 times the water Europe needs for the agriculture, for its nutrition, if we wanted to abate all the CO2 with power to X. Not to speak about the electricity that can be saved if we don't produce the CO2 in the first place by doing grave-to-cradle carbon circularity. Now, for an example, a municipal waste plant that matches its carbon output with natural gas pyrolysis shows you that if we wanted to get the hydrogen from an electrolysis we need an investment. If we build an incinerator, we need an investment. But if we do carbon circularity and blue hydrogen, we need practically just half the investment. On the CO2 side, we have an effect from carbon circularity, which you don't get if you just make hydrogen by electrolysis. And from a second carbon life cycle, we get another carbon saving, which adds actually to the carbon saving you can achieve from electrolysis. And I just took an average value of 25 tons per ton of hydrogen from the Hydrogen for Climate Action in Europe. So the example is, if I take 100 plants with 100 kilotons per year municipal waste, I get a certain amount of pyrolysis carbon, green carbon. I match this up with the natural gas carbon, and I get 5.5 million carbon to be used. Water-wise, we have a tremendous positive effect.
Stefan, sorry, this is Christopher. I could listen to this all day, but I need 2 minutes and need you to finish in 2 minutes, I'm afraid.
We'll get there, okay? So then, if we use these 5.5 million tons of carbon for the different applications, including a pyrolytic carbon soil enhancement, we can do this carbon neutral. Now, this project case, this example, just is 1.5% of the totally available biomass for energy use, which I took from this. And actually, if we look at the European energy situation and what the electricity component in it is, if we would produce our electricity from a methane pyrolysis hydrogen only, we could get almost the same electricity, and we could use the carbon to make synthetic jet fuel, which burns free of volatile particles. And I think that gives a lot of hope, because looking at it from that side, the combination of carbon circularity and methane pyrolysis from the natural gas, we can cover most aspects of the Green Deal and the circular economy. So anyway, there's a lot of details on the slides that, as I understand, will be provided. And for time reasons, I will leave it with that.
Stefan, thank you very much indeed for that presentation. It was absolutely terrific. I've got endless questions, and it's clear we're not going to be done today with all the things we would like to do. Chris, engineering manager from, Christopher Brandon from the EH Group. Chris, the floor is yours.
I'm the co-founder of EH Group Energy, based in Switzerland, currently in Singapore. As we've all been discussing, we obviously realize that hydrogen will play an important role in climate change mitigation, but one of the main challenges has been in realizing its potential in decarbonizing our economies is how to produce it at scale, cheap.
Chris, could you open your camera, please? The button on the top right-hand side. We can't see you and it makes it easier. Great, thank you. Perfect, thanks Chris, perfect.
I exist. The challenge has been how to produce hydrogen at scale, cheaply and with minimal emissions. So at EH Group Energy, we've been working on an innovative pyrolysis technology, splitting natural gas to hydrogen and solid carbon. So as has been well covered already now, hydrogen production, well-established business, 70 million tons produced annually. And as Stefan was mentioning previously, if it does go to fulfill its potential in the hard-to-abate sectors of transportation, industrial energy, building heat and power, we could see a 10-time increase in hydrogen production required by 2050, if not greater. But this is a messy business. Production of 1 million tons of hydrogen with SMR, which is effectively what we use for the vast majority of our hydrogen production, generates 8 to 9 million tons of CO2. And the hydrogen sector globally produces enough CO2 as the whole of the UK plus Indonesia combined. So what are the alternatives? We've discussed electrolysis, and I think this is also touched on by Alex earlier, that electrolysis using the grid as it is not a good solution. This is by Bloomberg NEF recently. Obviously with renewables, different kettle of fish. And the current scenario with gas SMR or gasification of coal, clearly not the way forward. Which leaves us with CCS or pyrolysis. So turning into the three, again, this is something that has been touched on. Electrolysis and all these technologies will surely, have room in the production of hydrogen ahead. Electrolysis, however, very high energy capex. It's 286 kilojoules per molecule of hydrogen. With SMR, it's in the region of about 63 kilojoules, so much less. But then when you start looking at SMR with carbon capture and storage, obviously the geographic limitations, but you also end up using a lot of energy to pump that carbon dioxide back into the salt caverns or whatnot. Which leaves us with methane pyrolysis. And there the challenge is that we're at low TRL, so technology readiness levels. So by and large, this is a very niche sector with, I would say, realistically half a dozen serious participants in it at the moment. But there's a tremendous opportunity to generate hydrogen with high value carbon byproduct. But we have taken a new approach to pyrolysis. We are doing hydrogen stripping using microwave initiated catalysis. So this is based on groundbreaking work which was developed at the University of Oxford's Inorganic Chemistry department over the previous 5 or 6 years. So we've filed several patents, and in all our work we're using inexpensive, abundant catalysts, typically focused on iron. So the process is that methane or any other fossil fuel passes over the catalyst bed, and microwave energy is aimed directly at the catalyst. And here the idea is to activate the catalyst to heat it up uniformly rather than a thermal process which heats the fossil fuel as well and the whole thing. This means we're able to work at much lower temperatures than other processes, so 350 C up to about 600 degrees Celsius to get the required catalytic decomposition. What's the result? It's practically nearly instant separation of methane into hydrogen and the resulting carbon. So we get very high hydrogen selectivity. In fact, with methane, it's like over 99%, which means just traces of CO and CO2, really traces. And these numbers were based from publicly available information, so have been improved since then. Originally, 2-3 years ago, we were getting the catalyst to work for about an hour and a quarter, getting good yields of about 80% till that catalyst needed to be regenerated. We in fact did our experiments across the whole spectrum of fossil fuels, starting from crude oil, working our way down to diesel and gasoline, all the way to methane. As you see, with the heavier fossil fuels, the selectivity isn't as high, although still around 80%. But with even with diesel and if you look at methane, it was at 99.8%. So what are the advantages versus the conventional thermal process of pyrolysis, which Alex touched on previously, and Stefan as well? What we're looking here, this is a non-contact, rapid, and selective heating of the catalyst. So it's an energy transfer rather than a heat transfer. So we're really just trying to activate the catalyst, which enables us to have a quick startup, a quick shutdown, and a much more uniform heating of the catalyst itself. That in turn leads to much higher levels of safety and automation, and the microwave energy in a microwave tunnel can be optimized with waveguides and so on to really apply the energy directly onto the catalyst solely. Okay, that's not what the slide looks like. But I'll tell you what it should look like, is that net energy balance is effectively, in this case, is the enthalpy of combustion of produced hydrogen divided by the electricity you're consuming. So typically, with the other pyrolysis approaches, and obviously with SMR and so on, you have to put a lot of energy in to separate the hydrogen. In our case, we're at 20 times higher net energy balance values than a conventional pyrolysis process. And in fact, theoretically, we could have a greater than 1 net energy balance, because the enthalpy of the hydrogen is greater than the electricity we're using to split the hydrocarbon. Okay, I guess we've lost this picture as well. On the other side of the equation, we are getting high-value carbon materials. So we're actually getting the full spectrum of carbon black, which can obviously use in tires, inks, agriculture, needle coke for industrial processes, graphite, carbon nanotubes for battery technology, and somebody had been discussing on the chat, you could also consider just putting the carbon and leaving it back in the ground where it originally came from. Okay. In our results, in fact, and it's a shame the image isn't there, but the image is not there. The vast majority of carbon that we get are actually high purity multi-wall carbon nanotubes. This is obviously a small market, but a very lucrative market. But you end up having to sort of tweak your process, whether you want to be focusing on producing the carbon nanotubes or optimizing for the production of hydrogen. Cost of production will depend on the price of natural gas, of course. So at the moment we're somewhere about $1.75 per MBTU. The image that isn't an image on the right shows our break-even, would have shown our break-even cost of carbon, so that we are equivalent with SMR. So at the moment, given where we are in our technology development, that would be about $4 per kilo of carbon. So for most markets, that would be absolutely fine. For carbon black, you're looking, it's less than that, it's probably about half a dollar per kilo. For graphite, you're looking over $10 a kilo. And obviously anything like carbon fibers and so on, it's much, much higher. And again, this other slide has been shown, the study by BASF. The point is to be able to scale this up to really get to benefit from the economies of scale in production. Challenges remain, of course. The technology readiness level is low. We're around 4 at the moment, trying to get it up to 6 in the next 18 months. And the challenges from the technology point of view are how to manage the carbon deposition, how that affects the catalyst itself, how to harvest the nanotubes. Again, there's a lot of work to be done on microwave optimization, but these can be also, this is obviously a standard technology, but it can also be scaled up on the industrial side up to megawatt level. Reactor development and scaling up onto a pilot project size. Similarly, we're looking for signs that the hydrogen economy itself is ready to scale up, and a lot of these issues were discussed earlier. The standards are harmonized with investment mechanisms for producers, and that emission standards are set for heavy transport as well as decarbonization policies. But by virtue of this call and what's happening with the Green Deal, it seems clear that we're well underway on all of these. Our project team, who's lost its images as well, is a team of 10 working on this, including our 4 partners at the University of Oxford. So our path towards a decarbonised economy will require significant investments in emissions-free hydrogen production and infrastructure. Electrolysis and CCS. Yeah, you got 10 seconds. Electrolysis and CCS will both surely have a major role to play in that effort. However, we believe that it will be possible to produce at scale distributed CO2-free hydrogen with high-value carbon byproduct via emerging pyrolysis technologies such as ours.
Thanks very much indeed. Our apologies.
Thank you very much for your time.
PowerPoint karaoke.
Questions.
But you did a great job.